I'll get in a rut eventually. All right, we're going to be talking about the rational method today, and I gave you a homework assignment last time, and the example we'll work in class today is going to enable you to solve that homework assignment, which is due on Tuesday. Now, we don't meet on Mondays, but of course you probably already know that next Monday is a holiday, so don't come to the engineering building then expecting people to be here, other than students doing their homework. But no professors will be here. We'll be taking the day off, water skiing, and laying in hammocks and stuff while you're working. So all is well in the world. Any questions about these announcements? All right. Well, the rational method is a way of predicting the peak runoff from an urbanized area. It can be used in rural areas, but usually it's not, and we'll talk about why that is. This is most commonly used in small urban watersheds that have a relatively uniform land cover. So the rational method is Q equals K CIA, and the K often is not referred to. If you'll see in various hydrology texts, usually they won't even bother saying K because it's just sort of a constant that you use for converting the units. But basically what it says is if you look at it, the units are a little bit strange. The BG, or the traditional units, work out in kind of a serendipitous way, that if you multiply the rainfall intensity, I is rainfall intensity, in inches per hour, so let's say the big storm we had last week, maybe that was an intensity at the peak of about 6 inches per hour. All right, and if you had a lot that had a concrete pad on it, let's say that maybe you have a concrete pad of about 0.1 acre, Q equals CIA, and then the surface C is referring to some sort of a coefficient for what fraction of the rainfall will run off versus the overall fraction. And so in concrete, maybe 95% of the rainfall will run off. 5% won't infiltrate through the concrete, but 5% would maybe be bound to the surface. It would be used to wet the surface. So in the case of grass, maybe it would be 40% of the water will run off rather than infiltrate or wet the surfaces of the blades of grass. And so C is a runoff coefficient. So we were talking about a concrete pad that's 0.1 acres. Let's say that concrete pad has a runoff coefficient of 0.95. So what I was saying is the units are a little bit serendipitous. We have inches per hour times acres, and this runoff coefficient is unitless, and what we're going to get is CFS. That will be the runoff in CFS, and so that's 0.6 and then times 0.95, so it's going to be about 0.58 or so CFS as the runoff from that concrete pad. And so it's called the rational method because it's relatively straightforward. All you have to know in order to predict the peak runoff is what is the surface like and what is the rainfall like. And one of the things about the rational method is it basically assumes that that the rainfall intensity is constant during the entire storm. And that's not necessarily true, but it's not a horrible thing to assume if you're trying to be conservative in your design. So the rational method is very simple. The other discharge estimation methods that you'll learn this semester are far more complex and time-consuming. And this is used as one of those so-called back-of-the-envelope calculation approaches, where if you're out in the field and you don't have much scratch paper, and it's not like you're going to download a bunch of data from the USGS or anything. If you're just in the field and you need a quick order of magnitude estimate of what the runoff is going to be, rational method is what you'd use. You'd say, well, I know in this area rainfall intensity may have a certain inches per hour based on the design level that you pick out, 10-year storm or something. You'd estimate the area, and boom, you could calculate a peak runoff value very quickly. Like I said, it's mainly for smaller watersheds, catchments less than 80 hectares in size, and the smaller the better, really. The larger watershed you apply this to, there's going to be more inaccuracy there. Time of concentration is how long it takes water to flow from one edge of a catchment to the other. So we were talking about a concrete pad, and if this is our drain for a concrete pad like a parking lot or something, think about all the water that falls onto that concrete pad is going to be traveling over the surface towards the drain. Well, to calculate time of concentration or to estimate it, what you have to do is you have to think about where is the point furthest away from that drain in terms of flow time. You know, maybe the flow is going to go all the way from here across the surface before it finally gets to the drain. And you have to know what the travel time is from the hydraulically furthest point in order to select the rainfall intensity that you use as the I. All right. We'll get into more about that in just a minute, but here's an assumption that's built into the rational method. Like I mentioned just a moment ago, the rational method assumes that the rainfall intensity during a storm is constant. But in reality, what storms usually do is they start off slow, they work to a peak, and then they taper off again. So this is time, and this is rainfall intensity. Usually it's just a few drops, and then it comes down to a heavy shower, and then it trails off to just a few drops again. And so that's one of the deviations between reality and assumptions in the rational method. And because of that assumption, it assumes that the runoff hydrograph, by the way, is a graph of water, hydrograph. And so it's how much water is coming off of that parking lot at any given time. So what you see is that the runoff from the parking lot is slow, and it's gradually increasing, and then it's constant. And that's not realistic, but it's just a consequence of the fact that we assume the rainfall intensity is constant when we are using the rational method. Our more sophisticated methods that we'll learn later in the semester get us away from some of these simplicities. So here's how you apply it. We've already applied it. You find what the time of concentration is so that you can pick the right rainfall intensity. And in the example we worked today in class, we'll do that first step of dealing with the time of concentration. So once you've got I selected, then you characterize the surface and you select a C value based on what is in the area. And when you go out into the field for the project, you're going to stand in front of somebody's lot and you're going to look at their roof, you're going to look at their driveway, their yard, their garden, the grass, and you're going to estimate how much of the area in that yard is different things. You're going to say, using an aerial map, you'll trace the lot and you'll say, all right, this is a 0.2 acre lot. And of that 0.2 acres, it looks like 40% is impervious due to the roof, 20% is impervious due to the concrete walkway, and the remainder is grass. You just do a quick breakdown of it. And so you'll come up with like a weighted C value when you're doing the project. And that's what this step is referring to. And then solve for the flow rate using the rational method. So any questions about this slide or the basic concept of the rational method, Chris?
Dr. Waite, K is rainfall intensity or actually I?
I, yeah. So K is a conversion factor that you'd use if you're using traditional units or SI. And, yeah.
Thank you.
Mm-hmm. Yeah. All right. So here is a look at some typical C values. And you can see that the way the rational method works is it would give you a different C value for a 2-year storm than, let's say, a 25-year storm. So basically, think about an asphalt surface. What they're saying is that in a 2-year storm, 73% of the rain on an asphalt surface will run off. But in a 25-year storm, 86% of the rain will run off. So is that because the surface itself is changing and adapting based on the intensity of the rain? I mean, is it like some sort of a transformer parking lot that is able to become more or less permeable based on the rainfall that it senses? Why do you think there's that difference between the fraction of runoff versus the return period of the storm?
Probably raining harder. So later your storm more.
Well, it's definitely, yeah. A 25-year storm is a storm that's so intense it only comes around once every 25 years, statistically on average. So it is a more intense storm. You're right about that. So why is it that during the more intense storm, instead of having 0.73, 73% runoff, you're having 86% of it running off?
Because there's like 76 storm rain is coming down at one time, so
Yep.
it doesn't have time to stick or
Exactly.
sink in.
Right. And so, like I mentioned very briefly before, some fraction of the rain that falls, that first little bit, is wetting the surface down. And once the surface is wet, then additional rain will cause the runoff. And so in a 2-year storm, like about what they're implying is that 27% of the rain is required to wet the surface, and then the remainder is runoff. But in a larger storm, in this case the 25-year storm, only 14% of that rain is required to wet the surface, and then the rest runs off. And so what these differing C values as a function of return period are referring to is the fact that it's not the surface itself is changing, it's just that on a relative basis, less of the precipitation is required to overcome those initial abstractions. All right, so that's one effect I wanted to point out. Of course, the other is that concrete or asphalt has a higher C value than grass. Now that's probably so obvious that we don't even need to discuss it, but I will anyway. Grass is going to allow for more infiltration because there's a more direct pathway between the atmosphere and the soil. If you've got 3 inches of concrete between the atmosphere and the soil, then the water can't get through there quite as easily. It's got to find cracks in the pavement in order to infiltrate even just a tiny fraction through. Okay, so that's an obvious thing. Now what about slope? Who can describe what the trend is as it relates to slope of the surface and explain maybe why? What's the trend and why when it comes to slope? Bert, what do you think?
I guess with the slope, there's...
First describe the trend. So what is the trend? If it's steeper, then...
If it's steeper, then there's more runoff.
Okay, so a steeper surface leads to more runoff. Now why would you just guess that might be?
The water can't stick as well.
Okay, yeah. It can't infiltrate as well or stick to whatever the surface is. So if it's blades of grass, a really steep slope, then there's going to be more of the tendency for that rainfall to continue over the surface than be bound to the surface of the blades of grass. And there's less time for it to infiltrate. And so the trend is steeper slope leads to more runoff. A flat slope allows infiltration. Water can puddle, and puddles help to force the moisture underground. A pool of water is going to increase the hydrostatic pressure, forcing the water through the soil grains and into the ground. And so if it's steep, the puddling and the pooling can occur. So I think that covers most of the trends that are relevant here. These C value tables are all over the place. Every book has a slightly different C value table. One that I've been using a lot lately is put out by the U.S. Department of Agriculture. They have something called the National Hydraulic Manual. It's pretty authoritative, I suppose, but what's really more important is just to understand the trends and find something that fits the surface that you're characterizing. So sometimes that's hard to know, should I use forest or pasture? You know, how many trees does it take to transition from a pasture to a forest? Doesn't look like the effect is too dramatic, you know, 36% versus 34% for the 5-year storm. But these C values is the biggest weakness of the rational method. The hardest thing about applying this method accurately is picking a good C value. And so the best way to pick a good C value is to calibrate the model. It's to go to a parking lot somewhere and measure the rainfall intensity and measure the water coming off the parking lot. So you have quantified in our Q equals CIA. If you went to a parking lot and you measured the Q and you measured the A and you measured the I, then that's the best way to get a C value. It's not to just look it up off of a table. It's to go to an area and actually calibrate what the C value is for the type of surface or the type of land area that you're interested in. All right, so I'd like you to get a chance to use the rational method. Let's assume a 5-year, 24-hour storm has a peak intensity of 95 millimeters per hour. And we've got a catchment, meaning a watershed area that has parking, lawns, and a rail yard, and single-family housing. And so let's estimate the peak runoff for that. You're going to have to guess. I mean, there isn't necessarily an entry on that previous table for what to use for single-family housing. And so use your best judgment, and then I'll show you what my best judgment is, and that'll be a good illustration for the relative weakness of the rational method. So let me flip back to the previous slide so you can see the C values a little bit more easily. You've got the problem statement there in front of you in the notes. Yeah, there's a little bit of wiggle room on the rail yard and the housing. For the rail yard, I picked 0.6, just looking at like what's undeveloped land like, and thinking it probably has some buildings on it. And plants usually help infiltration, where bare earth isn't as good as plants, because a grassy area, for example, having the roots penetrating down into the surface sort of provides a pathway for the water to get into the ground. And so, my C value of 0.6 for the rail yard, 0.5 for the housing, calculating that composite C, those are guesses, and I wouldn't say that a different guess was wrong or right necessarily. So what I get is 17,860 cubic meters per hour when I use a composite C value of 0.495, 0.095 meters per hour for the rainfall intensity, and then there's 38 hectares times 10,000 square meters per hectare. So that puts this in meters per hour, this is square meters, and so the units we get out of that is cubic meters per hour. In terms of cubic meters per second, that's 4.96 cubic meters per second. All right. Well, let's go back to that slide so there isn't any uncertainty. Well, where are we? All right. So if we do it in traditional units, you get CFS for Q, CIA. Okay, C is unitless, I is inches per hour, and A is acres. All right. Now, in reality, there is some conversion factor of 1.008, but that's so close to 1 that we ignore it. I mean, if you were to actually multiply inches into feet, and acres into square feet, it would be off by a little, but it's close enough that it's not worth worrying about that conversion factor. That's traditional units. For SI, what you'll notice is that the units, if it is millimeters per hour and kilometers, then you'd need to have 0.26 in order to get cubic meters per second. So what we have is the K value, and what it basically is doing is it's converting, C again is unitless, and we're going to use intensity of millimeters per hour, and the area is in kilometers squared, and then what it shoots out is going to be the runoff in cubic meters per second. So that K value is 0.28 because there isn't that same serendipity of inches times the conversion of hours to second times how many feet in an acre. It just sort of works out in the traditional units. But over here, I already had my intensity in meters per hour, and I converted the area into meters, and so no conversion is necessary to get into cubic meters per hour. But to get it into cubic meters per second, of course, then I have to divide by 3,600. Yeah.
Just for your opinion, like, what kind of storm do you think the flood here in 1937 was? 100 or 500 years storm?
I don't know. They probably have the rainfall data for that, and when we get to rainfall, we can look it up. What we'll do is we'll look up the rainfall on that day because I've got access to the rainfall records for the Huntington area going way back, and then we'll look at what's called an intensity duration frequency chart that has a graph of how big of a storm qualifies for what return period. So we'll look that up if you'll remind me. That's a good question. Based on the damage that it caused, it sounds like it was probably around a 100-year storm. Okay, well, applying the rational method into hydraulics is where we're headed next. You've already sized pipes before based on flow rates. And so the relationship between hydraulics and hydrology, you've already done the hydraulics, but there's this boundary. Just conceptually speaking, what the hydraulic engineer does is you take Q and you size the pipe, or size the pipe network. So basically the calculations you do in hydraulics is for some flow rate, how big does the system need to be? What the hydrologist does is says what the Q is based on watershed characteristics. And so the easiest way a hydrologist can say what the flow rate is going to be is that rational method that we just learned. And that's essentially in 3 easy steps the job of a hydrologist. Never mind that the results aren't too accurate, but it'll get the job done in any case. So this is sort of how the two link together, is the hydrologist would look at a watershed and estimate the runoff, and the hydraulic engineer would take the runoff that had been mentioned by the hydrologist and then size the pipe. This example that we're going to work has both of those steps built into it. In an urban area like this, what we're looking at is a neighborhood with a pipe network system. And you'll notice that it has contour lines here. And the contour lines are the ground elevation. And the elevation at different spots in the system is identified. You know, here at this point is 732.3 feet. We know the street names. And what they've also done is they have, with these break lines here, identified where the water is flowing to. These circles represent inlets to the system. And so any rainfall that is in this area, in these boundaries, is going to flow to inlet 1-1. The water that gets into inlet 1-2 is in this area. All right. Inlet 2.1 is everything from this dashed line over to the boundary, over here, down, sideways. Sometimes these boundaries are a little bit artificial. They're probably taking into account where the break lines are in elevation, if there's a high point in elevation, It might be based on if there's a curb somewhere. The curb can force flow one direction that it might not ordinarily go. Different surfaces, like if there's a concrete sidewalk, that can intercept flow and redirect it a certain way. But somebody here has already done the job for us of identifying what contributing area goes to each of the inlets. All right. Now what about this numbering system that they've got here? 1.1, 2.1, 3.1. So it seems like every time you go further downstream, they're increasing that first number. And 1.2 would be it's dumping into the second inlet here. I'm not quite sure of the naming convention, but in this example, what we're going to do is we're going to work an example where we're already given the C value and the area for each of these subbasins. And also in the example we're going to work, what's defined is the area, the slope of the pipe, the length of the pipe. We're going to go through a process of calculating what is the peak flow rate that will get to there, and then how long does it take to get through the pipe, because we know the size of the pipe is going to be calculated by us based on how big it needs to be to accommodate the flow. And I've put together a spreadsheet template that has some blanks in it, and basically what I'll ask you to do is go through and solve the first couple of rows by hand, and then once you've done that, I'll show you in Excel how it can be solved in sort of a more automated way. And in fact, I'll open up the tablet cart so that you can have access to Excel once we've gone through and done it by hand a couple of rows. So let me get this to you. All right. So what you need to do is implied by the structure of the spreadsheet. Let me turn to my copy of the spreadsheet and we'll talk through it. Were there any extra copies? You got one? Thanks. All right. So one of the first things to point out is that this other figure besides the neighborhood on the front page is a chart that relates the duration to intensity, the storm intensity. And so if you were to estimate that it takes a certain amount of time to travel over the land, like from this boundary to get to the catch basin, if that was a 10-minute travel time, then what you could do is you could go to 10 minutes on the intensity curve, go vertically up to where that line intersects the curve, and then go over, and it looks like about 4.25 inches per hour if the duration was 10 minutes. And so on the second page of the spreadsheet, what is provided you is the name of each pipe. And so on the printout I've given you, the pipes are labeled as pipe A, B, C, D. On the figure here on screen, they're not labeled in the same way, but what you need to do is fill in the blank for what's the upstream junction, the downstream junction, and the contributing area has already been defined for pipe A. So here it says, for example, 2.2 acres is the contributing area that goes into pipe A. So that's referring to this watershed boundary. That first upstream segment is 2.2 acres. And it's also provided that the C value is 0.65 for that area. And so what you need to do is multiply C times A, and then the sum of CA is actually relevant when you get to an area like 2.1, because when you get to an area like 2.1, this has not only if you think about the pipe C, so if you turn to the front page, you'll see that in the handout, this pipe is referred to as pipe C. So how much upstream area is feeding into that pipe? It's got the water that's coming into the network here, but it also is going to get water that's coming into the network there and there. And so the purpose for that column where it says the sum of CA is that in pipe C, you're going to need to add the CA of what flows into junction 2.1 and also the CA that goes into 1.1 and 1.2. All right. The time to inlet is basically the travel time over the land. And by the way, of course, there are these notes at the bottom here that defines each of the columns as you're going through the example if you forget what one of the columns was supposed to be. So the travel time is what you're going to use in order to understand what the intensity should be. And in fact, the intensities have already been picked out for you here in the I column based on the timed inlet that's shown there. The next thing, the time of concentration, is going to be the inlet time plus the upstream flow time. So the time of concentration for pipe C, for example, the time of concentration is going to be the how long it takes to flow over the surface. But then there's another thing that you have to consider, and that is how long does it take to flow just over the surface to junction 2.1 versus how long does it take to flow over the surface into junction 1.1 and then travel through the pipe. Because those are two different routes to getting water into pipe C. It maybe came from over the surface into the junction, it could come from over the surface into there, or it could actually come into junction 1.2 as well. And so having the T sub D column, which is the column that allows you to find the time of rainfall distribution, it's either going to be the time of concentration or the largest of the three time of concentration options. So there's going to be three different times of concentration for pipe C, and you pick the largest of those three to put in as the T sub D. All right, so when you finally have that, then you can calculate the Q with Q equals CIA, because you'll know the sum of the CAs, and you'll multiply it by the I in order to get Q. And then from that, it's hydraulic design using the equation that's down at the bottom there, the required diameter, and then you round up to the nearest pipe diameter that's actually available. So if it was saying that you needed a pipe diameter that's 1.1 feet, then you'd have to round up to whatever the equivalent diameter is for a 15-inch pipe, and then calculate the flow velocity and the flow time. So this is a pretty detailed process to do by hand, but the reason why it's important to do by hand is this is the underlying logic that StormCAD uses. And understanding this is going to sort of unlock the keys. It's how you earn the keys to the car in order to use StormCAD is to understand the logic of how it's working in the background. So I'll stop talking and give you some time to start sorting through this and reading the definitions and trying to figure out what goes where. Let's go through this together very briefly. Just in case you're not quite sure how to do this. Yeah, no, that was the wrong one. All right. So the upstream junction and the downstream junction is pretty easy to figure out. I can't see that. And then C times A is just the runoff value that indicates how pervious the surface is, multiplied by the area that's given. Now the sum of CA, if you look at the map that's provided, since pipe A is only getting flow from one inlet, it's going to be the same as the C times A. And the same is true for pipe B. Pipe B only gets flow from one inlet, so CA and the sum of CA are the same. But now for pipe C, it gets flow from, pipe C is going to get flow from its inlet and also from pipe A and pipe B. And so the total sum of the C times A is the sum of all of the CAs for what's upstream of it. So is everybody with me so far? All right. Now, in time to inlet, it's given how long it takes for the water to flow over the surface. And so it's given that it's 11 minutes to get into pipe A through junction 1.1. This 13.7, that's how long it takes to flow from this edge over to the inlet. So that's given. What we have to do now is take a look at the time of concentration. Now the time of concentration is going to be that same 11 minutes here because there isn't any alternate flow route that has to be taken into consideration for pipe A. And likewise it'll be 9.2 for pipe B. Now it's 13.7 is how long it takes to flow over the surface, but then remember that there's a couple of different flow paths from to get into pipe C. There's what's getting in directly, and so that direct has the time of 13.7. If you look over here, it's the 11 minutes is how long it takes to get there from 1.1, and then we have to put in the 9.2 because that's how long it took to get from pipe B, or get into the system through junction 1.2. So we write that in there. So it is 13.7. 13.7 is the time here, and the upstream flow time, that's how long it takes to travel through the pipe before it gets to pipe C. And so from 1.1, we're provided with the travel time from this inlet to that one. And the 1.4 minutes means that the total time of concentration is going to be 12.4, because that takes into account the flow over the surface of 11 minutes and then the flow through the pipe of 1.4 minutes. Okay, so here we know the flow through the pipe, it's 1.3 minutes to travel through pipe B until it gets into pipe C, and then there was also the time over the surface, and so we add up the two and get 10.5 as the time of concentration via 1.2. And now what we choose as TD is the largest possible T sub C for that particular pipe. Now pipe A only has flow coming in from one route, and so it's 11.0 minutes. 9.2 minutes because it only had one route. But now here we need to pick the largest of the three. So whatever takes the longest is the one that governs. So it's going to be 13.7 because what takes the longest, the three options for water getting into pipe C, there was option 1, which is flow over the surface, option 2, which is flow over the surface then through the pipe, or option 3, which is flow over the surface into the pipe and then finally getting to pipe C. Of those three, what takes the longest is just the overland flow directly into junction 2.1. So that's why we've picked 13.7 for that TD. Now, the TD is what was used to select the rainfall intensity, the time to duration. And so these ones that I've already provided for you are based on the correct TD. And so the way that you find QP is it is going to be the sum of the CA, and so this was 1.43 times the intensity of 4.00. And if we multiply those together, I think it should be 5.72. Can someone double check that for me? Somebody with a calculator handy? Okay. So then to get the correct peak flow going through pipe B, it's going to be the sum of the CA, so 0.96 times the intensity. Now why is the intensity higher here? Why is it 4.3 inches per hour instead of 4 inches per hour for pipe B? Anybody know why we've got a higher intensity there? It's because it's got a shorter T sub D. The water gets to that junction faster. And so since it can get there faster, there's a higher rainfall intensity. So if you look, the shorter the duration on this curve, the higher the rainfall intensity. And so that's why there's 4.3, why it's higher than the 4. And down here where it's 3.6, it's less intense because it took longer to eventually get to that pipe. So what you need to do to fill in these blanks is you multiply the CA, the sum of the CA, times the intensity. So for this one, it's going to be 4.13. For this one, 18.84, because that is the 5.12 acres times C multiplied by the rainfall intensity. Now I know this seems confusing, but the only thing more confusing than this is not having the template and trying to figure it out without the template. So that's how I had to handle it. The book doesn't give you the structure like this. Yeah.
So with the, like, what does the rainfall intensity vary? Like,
Yeah.
I see this graph.
Yeah. All right. It starts raining. Let's assume it's raining over the entire area at the same time. But the water is getting into pipe C at different times. And so we use a different intensity because what happens is, if you think about an area, you've got an area, and let's say it starts raining on the area. It takes 10 minutes to travel from the furthest point to the grate. 2 minutes into the storm, only this amount of the area is contributing. And so you're not going to get very much runoff quite yet, because even though it's raining really hard, only a small fraction of the total area is contributing. And so another 2 minutes, so 4 minutes later, all of a sudden you've got this much of the area that's actually contributing the flow to that inlet. Because, you know, the water is traveling over the surface, and so it takes a while for the water to actually reach the inlet. And remember, in the rational method, what we assume is that it starts raining and it rains at a constant intensity the whole time. So it's not like, in reality, the rainfall intensity varies, but in this model, in the rational method, we're just assuming a constant rainfall intensity. And so when are you going to get your peak flow rate? You're not going to see the most runoff from that catch basin until the entire area is contributing. And so that sort of ties into your original question of, you know, why are we using a different rainfall intensity, is because it takes a different amount of time for the entire area to be contributing. And so however long it takes for the whole area to be contributing is the rainfall intensity that you select for the system. I think you'll understand that more when we get beyond the rational method and start accounting for the temporal distribution of rainfall, you know, acknowledging the fact that rainfall does vary over time. But I think for now the short answer is you use a different rainfall intensity just because the bigger the area, the longer it takes for flow to get there. And so we're designing this sort of for a worst case scenario. And if you've got a small area that takes less time to concentrate, then you have to worry about a big intensity. But if you've got a large area, you're contending with the area as being the primary driver for the runoff, but you've got a lower rainfall intensity because of the longer time of concentration. So that's all I can give you for now to explain it. But what you need to do at this point, once you know the peak flow rate, to calculate d sub r is you use the equation that's provided here. This is basically Manning's equation, just rearranged to solve for diameter, the required diameter of the pipe. Okay. We finish at 10:45, right? Well, all right. I don't think you'll have time to start up Excel, but I'll show you my Excel spreadsheet, and then I'll email you a PDF of the solution. I won't email you the actual Excel solution because I'd like you to set it up yourself. You know, having this on hand, it's one of those things where if you have the spreadsheet for the example, then it'll probably be useful for you on the homework. And so let me show you. Let's switch back over to the other screen. QN and QP, where do you see QN?
In the equation down the bottom, D or...
Oh, Q is the flow rate, QP, yeah, and then N is the N value for the pipe.
Oh,
yeah.
Q times N. Okay.
Right, yeah. So N here isn't a subscript. In this example, what we're assuming is that the N value of the pipe is 0.014. That's at the top of the, at the top. All right. So let me just dim the lights a little bit so you can see the screen a little bit better. All right. Okay, so we know the pipe length. We're given the slope, the junctions, the areas. Sum of the CA is just going to be the CA itself if it's like a pipe where there's nothing upstream of it. But this one was the sum of all of the CAs because all of those areas are feeding into pipe C. Okay, the time to inlets, those are given, but then for this one, it is referring to the time of concentration of the upstream pipe. So here where it says the flow route is from 1.1, that's how the water is getting into pipe C. You know, here what we are designing is pipe C. And so water gets into the pipe C either overland from 1.1 or from 1.2. And the upstream flow time that's mentioned there was calculated in this part of it, like where I put in Manning's equation to solve for the diameter required based on the peak flow rate. So there's a diameter required, and then you round up to the next nearest increment of available pipe size. In this case, 1.25 is a 15-inch pipe. And then the flow velocity, that is finding the flow rate, flow velocity, cross-sectional area. So it's V equals Q divided by A. So the area, the flow rate, Q divided by A. And then the travel time uses the flow velocity and the distance, the length of the pipe. Okay, so we can do that for all three of the pipes, and this, probably the hardest thing to keep track of is that there are three different time of concentrations for pipe C. There's the time of concentration based on the Overland Flow route. There's the water coming via 1.1, which has 11 minutes at the surface, and then a travel time of 1.39. So this travel time here we take down to there. I should actually just have it refer to that cell. Rather than typing in 1.4, I should just have it refer up to that. Okay? And so here, it's referring to the flow time upstream. And then we take the longest of the three in order to find the intensity, calculate the peak flow rate, size the pipe. Okay, so let's reinforce that at the next pipe. Let's look at what's going on here at pipe D. Okay, at pipe D, you've got just only water that's coming in through junction 2.2, and so it's sort of like nothing's upstream of that. The area is given. The C value is given. The CA is just going to be C times A, and the sum of the CA, since there's nothing additional upstream, is just going to be the CA. The time to inlet is provided, and then you can calculate the time of concentration is the same as the time to inlet for that pipe because it's only overland flow, and the T sub D is the biggest of if there are multiple routes. In that case, there's only one route for pipe D. Now pipe E has water coming in from 3 different locations. The water coming into pipe E is coming overland via junction 2.1 and via junction 2.2. And so each one of these has a different upstream T sub D. So from 2.1 we take the previous T sub D that was this one, and it drops down to there. So that's how long it takes the water that's actually coming via pipe C. And this is the water that's coming via pipe D. So we use the T sub C that was there before. And select the biggest of these 3 to be the T sub D. Look up the intensity based on that, and then it's the same process of using Manning's equation to calculate the peak flow rate. I'm sorry, no. Q equals CIA gives you the peak flow rate, and Manning's equation is what gives you the diameter that's required for the pipe. So I'll email you a PDF of this solution so that you can set it up in a spreadsheet if that's helpful to you for the homework. All right. So we need to talk a little bit about overland flow. And overland flow occurs when the rainfall rate is greater than the infiltration rate for the soil. So when water is falling onto the surface faster than the soil can allow it to percolate down into the soil grains, then it starts to flow over the surface. And sometimes it's called sheet flow. It can be called surface runoff. But it's essentially the movement of water over the soil or the ground surface before there's clearly defined channels. Once you have channelization, then overland flow doesn't apply any longer. Once you have channelization, then you have to use like Manning's equation to calculate how quickly and what the depth is. But overland flow is just the movement of a sheet of water over the surface before it becomes concentrated. And there are a couple of different methods that are used to calculate the time of concentration. And what I want to point out to you, more than having you write down or memorize these equations, the important thing is to start to get familiar and acquainted with what they take into account. Because these different time of concentration equations have varying levels of sophistication built into them. And so the question is, how long is it going to take for water to flow a certain distance over the surface? And what this kinematic wave equation takes into account is the fact that the roughness of the surface may have an impact. And so you'll notice that this has the Manning's N value in the equation. And so a very rough surface is going to have a longer flow time than a surface that's smooth. A very smooth concrete is going to allow water to flow as a sheet over its surface much more quickly than like a rough, hardy grass. So N is built into the kinematic wave equation. Length obviously will be there. If there's a longer flow distance, then that's going to increase the flow time. Slope is accounted for, and we've already talked about the slope effect today, that if you have an increased slope, the water is going to move more quickly over the surface, and so here slope is in the denominator, meaning that big slope is going to decrease the travel time. And the same is true with the rainfall intensity. This is saying that the more intense the rain, what they're taking into account here is that a more intense rainstorm is going to have a greater water depth, and then more of your flow depth is further away from the resistance of whatever the surface is that's resisting. So if it's a concrete surface, if you have a deeper flow depth, then more of the cross-section of the flow is further from that resistant surface, and so that'll decrease the travel time. So the thing to point out is that this actually is an iterative approach, because you don't exactly know what the rainfall intensity is going to be until you know the travel time. And so it's sort of an iterative process to actually use the kinematic wave method, where you have to assume some rainfall intensity, calculate the time of concentration, and then you'd find the actual rainfall intensity from the intensity, duration, frequency curve, and then you go back and you solve it again the second time. So it begins with an assumption before it converges on the actual travel time. Here are some N values that are given for overland flow. N values will be a little bit different when it's overland flow versus channelized flow, because in overland flow the water depth is very shallow, and so it seems that there's more resistance that's imparted to the liquid as it moves than if it was channelized flow and the water depth was greater. There's another method called the NRCS method, and it, like the previous method, is limited to relatively short distances, because once you have very long of a distance, if you have more than 100 meters of surface flow, then it begins to form channels. And if you're out in the woods, you can probably see that. The water, and when it's raining, will flow over the surface for a while, but then it starts to consolidate into little streams, and those little streams start to tear into the hillside. And so sheet flow can only be assumed to occur for a relatively short distance. And so what does this equation take into account to answer the question of how long does it take to travel a certain distance? Well, length is a main parameter. Again, N value and slope. Here, P2, rather than inputting the intensity of the actual storm in question, this method just asks you to input what's the rainfall depth of a 2-year storm. And it's based off of that, rather than the intensity of the storm in question. So this is a little bit easier to use because it's not iterative. The Kirpich method takes into account, it's a simpler approach. You'll notice what's missing from here is in the equation they're no longer including the N value or anything about the precipitation depth. And so it's insensitive to how big the storm is. But since it doesn't have the N value, what they usually say is they have these correction factors. If you've got concrete or asphalt, multiply your travel time by 0.4. Concrete channel, then multiply it by 0.2. Or if it's grassy, flow in a grass channel, or general overland flow, double it. And so this is a lot less accurate than the previous equations have been, because it takes fewer factors into account in calculating the time of concentration. Izzard equation, if you look at what it's taking into account, it has a length factor and rainfall intensity, but it doesn't have directly in the equation slope. What it has you do is first select what's called a retardance coefficient based on what the surface is like, and that could be thought of as akin to the Manning's N value, where a smooth surface has a lower retardance coefficient than a rough surface, and then with the retardance coefficient you get a K value taking into account retardance, the intensity, and the slope. And so it's sort of an indirect taking into account the the factors that are in some of the other methods. Let me give you a handout that has a variety of these different methods mentioned. And in the homework assignment that you've got due on Tuesday, I ask you to, for the parking lot that's next to the engineering building, try applying a couple of these different methods to calculate the time of concentration. So there's the methods themselves. I had this example, and we won't have time to work through it, but we will have time to look at the solution, and that's really the important thing to illustrate for you is how different they really are. In this example, what I was saying is, let's look and see what's the time of concentration according to a few different approaches for the same area. And so we had some grassy area with a certain slope, a 1.5% slope, and a distance of 75 meters. So how long does it take for the time of concentration according to kinematic wave? So I solved the kinematic wave by putting in the n value, the distance, the rainfall intensity, the slope, and got 22.96 minutes. And since that's the most sophisticated approach, we can think of that as probably the most likely to be correct. Kinematic wave has a lot of factors that it's taking into account, but it's harder to use because it's iterative. NRCS is also considered pretty good, but look at how different the time of concentration is according to the NRCS method, about 52.5 minutes when you calculate it according to that approach. And so, I mean, that's essentially double the time of concentration to what kinematic wave was guessing. One of these other approaches is Kerr pitch, and Kerr pitch was, if you calculated, you get 2.66 minutes, but then you have to double it for Overland Flow, so 5 minutes. And the problem with the Kerr pitch approach, of course, is that it doesn't take into account the rainfall intensity or really, in a very meaningful way, the roughness of the surface. And so it really underpredicted how long it was going to take according to the Kerr pitch method. Izzard, 38 minutes. Kirby, which is another one of these methods, 18 minutes. And so you're going to see the same thing in estimating the time of concentration for the parking lot here next to the engineering building, that you get a wide variety of answers, and because you're making some assumptions for what the n value should be or what the flow path route is and therefore what the length is, I'm sure as each of you work, you're going to get a slightly different answer, and that's okay. I don't expect everyone to turn in the same solution. So before you go, let's just take one last look at the announcements. I think essentially the main announcement that you need to be concerned with is that the homework assignment is due on Tuesday, and then on Tuesday we're going to talk about the project a little bit more and start working with Stormcat. So we'll get into the Bentley software on Tuesday.